Welcome to this explainer. Today we're doing something really cool. We're popping the hood on the supercomputers sitting in our pockets right now. We'll break down the mobile architectures of both Android and iOS to build a crystal clear picture of what actually happens between the glass screen you touch and the raw silicon processing your commands.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the mobile mental model, then peek inside Android's layers, followed by Apple's iOS stack. After that, we'll map out the startup sequence journey, and finally, look at bridging code and hardware.
Section 1. The Mobile Mental Model.
At the very heart of this model, we've got the kernel. Think of it as the ultimate behind-the-scenes boss of the operating system. When we're talking about managing the physical reality of your device, allocating memory, picking which process actually gets CPU time, handling security protocols, and talking to device drivers, well, the kernel is the manager making all those critical calls. It is the absolute core of the OS.
Moving a bit closer to the surface, we hit the runtime. So if the kernel is the hardware manager, the runtime is the actual engine that brings your lines of code to life. It's the thing responsible for loading up that code, executing it, and, crucially, managing the memory that specific app needs, often sweeping up after it with a garbage collector.
And then, sitting on top, we have the framework. This acts as a vital bridge. It exposes these nice, clean, high-level APIs to developers. Things like turn on Bluetooth or show a notification. By doing this, the framework beautifully hides the staggering complexity of talking directly to underlying system services and raw hardware. Basically, it keeps us from reinventing the wheel every single time we want to access the phone's GPS.
Let's move to Section 2, Inside Android's Layers.
Let's see how this builds in the real world. At the very top, we have the physical hardware itself, your CPU, RAM, camera, the whole shebang. Right beneath that sits the Linux kernel, functioning as the foundational boss of the Android OS. Moving down, we hit the hardware abstraction layer, then system services, and then the Android framework. And finally, at the very bottom, there's your actual app, running on the Android runtime, usually called ART. It's a remarkably clean, linear delegation of responsibility.
So the crucial point here is really understanding the role of that middle layer, the HAL, or hardware abstraction layer. Think about it. Android runs on thousands of different devices from totally different manufacturers. The HAL brilliantly provides a standardized interface. It literally stops your apps from interacting directly with messy, manufacturer-specific hardware. Your app just talks to the Android framework, and then the framework uses the HAL to talk to whatever specific camera or Bluetooth chip happens to be inside that particular phone.
All right, shifting gears to Section 3, Inside Apple's iOS stack.
Looking at the iOS ecosystem, you are immediately going to notice the parallels here. Again, we start with the hardware at the top, but instead of Linux, iOS uses the XNU kernel. Right below that, we've got the Core OS managing low-level services like the file system. Then comes Core Services, providing APIs like Foundation and CloudKit. And finally, we hit the UI frameworks like UIKit or SwiftUI, which is what your actual application code interacts with.
And this brilliantly illustrates a major takeaway for us. Despite the totally different naming conventions and, the fiercely competitive branding out there, the fundamental structural DNA of both systems is almost identical. Android uses the Linux kernel, iOS uses the XNO kernel. Android uses the Android framework, iOS uses Core Services and UKit. It really is a shared philosophy of layered abstraction.
Moving right along to Section 4, the startup sequence journey.
I want you to imagine this for a second. You pull out your phone, you spot an app, and you tap it. It feels instant, right? But what exactly happens from the millisecond your finger physically taps that icon until the very first piece of UI, that first widget, is rendered on your screen? Let's break down this incredibly fast, split-second journey.
Here's the sequence on Android. You tap the icon, and the Android launcher catches that request. The OS quickly checks, hey, is this app already running? If not, it spins up a new process and an application object. Then it creates a launch activity, which is basically the core screen container for Android. If you happen to be running a cross-platform app, say built with Flutter, a Flutter activity is launched. That fires up the Flutter engine and the Dart virtual machine. Finally, the main function runs, and boom, your first widget appears. All of this literally happens in the blink of an eye. Now, compare that to the exact same sequence on iOS. It's practically a mirror image, just using slightly different terminology. You tap the icon, but instead of the launcher, a system called Springboard receives the request. A process and application are created, but instead of an activity, an initial scene is created. For a Flutter app, this means a Flutter View controller is born, which kicks off the Flutter engine, the Dart VM, and finally renders that exact same first widget.
Seeing those sequences side by side brings up a genuinely fascinating question, especially for anyone looking at cross-platform development. If tools like Flutter are built to write code once and run it anywhere, why do they still fundamentally need a native host like a Flutter Activity or a Flutter View controller to start up?
Well, the answer grounds us right back in our core architecture model. You simply cannot bypass the operating system entirely. No way! Android and iOS actually require these native components, activities and view controllers, as their basic, non-negotiable units for UI and lifecycle management. The OS only knows how to talk to those specific components. So frameworks like Flutter, they have to provide their own specialized subclass to sit perfectly inside that required native container. Ultimately, they're just guests in the OS's native house.
And that brings us to Section 5, Bridging Code and Hardware.
Now, let's take this somewhat abstract mental model and apply it to a real-world everyday action. When you press a button in a mobile app to take a picture, how does that request actually travel from your high-level application code all the way down to the physical camera hardware letting light into the lens?
Let's walk step by step down the Android stack. First, your code calls the Android framework's exposed camera APIs. The framework basically says, "I got this," and hands the request off to the underlying system services. Those system services then talk directly to the HAL, our hardware abstraction layer. The HAL takes that and translates it into the highly specific instructions needed by Step 4, the actual hardware driver for that exact physical camera lens.
Over on iOS, we see a totally parallel journey flowing just as seamlessly. Your application code talks to the Core Services layer. Core Services delegates the heavy lifting down to the Core OS layer. Core OS then communicates directly with the XNU kernel, and the XNU kernel acts as the ultimate manager, bridging that final gap right down to the physical hardware driver of the iPhone's camera. Which brings us to a final, slightly provocative thought to wrap things up. If modern cross-platform tools are so incredibly powerful, why don't they just replace Android and iOS completely? Well, as we've uncovered today, the answer is that they are ultimately just UI toolkits. Every single app, regardless of how it's built, absolutely relies on the operating system's architecture. Its kernels, its runtimes, its hardware abstractions, just to exist. You simply can't have the beautiful UI without that deep, complex architectural foundation supporting the whole thing. I hope this explainer is giving you a whole new appreciation for the incredible layered symphony happening inside your phone every single time you tap that screen. Keep learning, keep exploring, and we will catch you next time.